Hi everyone, welcome to the Chapter 5 review. Today we're going to review the periodic table and the main key concepts from this chapter and the homework questions that were commonly missed or misunderstood. Okay, so section 5.1 was about Mendeleev's periodic table. Here are our key concepts that the reading addressed. So basically, how did he organize the elements in his periodic table, and then what evidence verified that his table was correct and the usefulness of it. Okay, so this is what his periodic table looked like. He published it in 1872. So this question here, a lot of you missed it on the homework. Why did he leave some locations in his periodic table blank? How did he know where to leave spaces? Well, essentially, to answer this question, we first need to know how he organized the table. Okay, so he organized his table by increasing mass, so the mass of the atoms themselves. So if you see here, he starts with helium, and this image does a really weird job of portraying it, but basically there should be another line between like lithium and hydrogen. So he kind of like staggers them back and forth, but basically this is a row, and so on. So you can see he starts with the smallest, and then he goes to the right, and then comes down again, and then goes to the right. So he ordered them in increasing mass, and also he put elements that had similar properties in the same column together, okay? So similar properties are in these columns, also called groups, right? We organize it a little bit differently today, and I'll talk about that in just a minute. But basically, this question is asking, how did he know where to leave these spaces, right? So he's basically left these spaces saying, well, there should be an element here, and I think that it's going to weigh about this much, but we haven't found it yet, so I'm just going to leave these spaces here. So essentially, he knew how to do this because he followed his pattern that he was organizing it in, right? And he left these spaces blank based on that pattern. So he's saying, there should be an element here that has the same properties as the stuff in this group. Okay, so let me give you an example of how he did this, and hopefully this makes more sense. All right, so we're going to focus on bromine, all right? So he knew that bromine had really similar properties, and remember those properties are physical properties and chemical properties. They had really similar properties to chlorine. So he went ahead and he wanted to put it in the same group, this group 7, same group as chlorine, okay? But he had, of the known elements that they knew at the time, he could have put it right after zinc, okay? Because he did the same thing for zinc, put zinc in the column based on the similar properties as the other ones in group 2. And then he could have put bromine here, right? It would have made sense because 80 is bigger than 65. But he's like, well, it doesn't match any of the other properties in these columns. So I'm going to put it over here. And then as he was piecing this together, they also found arsenic, which is 75, and selenium, right? So he found these two, and he put these two in these two columns because they matched the properties in the columns, right? And then they didn't know which elements went in these spaces. So he left, logically, following his pattern, he left spaces in group 3 and group 4 so that later on when he or other scientists found these elements, they should fit right in here, right? This space should match the properties of boron and aluminum and all these other things in this column group 3, okay? And the same goes for this one. So all these spaces, he left them here because he was following his pattern by organizing them by their mass, increasing mass, and organizing them in these groups or columns based on their similar properties. Okay. this other question, what supported and validated that his methods of his organization of the table were actually correct? Well, remember he shared his table, his periodic table, with the world, his colleagues and the world in 1872, and he left a space right here, right under aluminum. He even named this Eva aluminum, I think, this unknown element. He's like, there's something that's got to be here, right here, that weighs about this much between calcium and tin. But he was like, well, I think there's something between these two elements, and it's going to have very similar properties to aluminum. Well, just 3 years later, they actually found a new metal called gallium. Okay, and gallium's that really like funky, weird stuff. If you remember watching that video where the guy puts the metal in a plastic bag and then melts it in his mouth. Also, if you were in lab the other day, we had a sample. Zoe brought a sample of gallium. So we got to feel what it's like, kind of really soft metal, and it melts at like almost body temperature. So you could put it in your hand like this and it melts and it feels really weird. So the discovery of gallium kind of proved that his organization method was correct. And it kind of proved to all of his colleagues that, like, hey, maybe this is something that we should follow and try to investigate more, right? So, yep, answer is gallium. Next up, we're going to talk about the modern periodic table. Let's jump right in. How is the modern periodic table organized? Okay, let's watch this short video and see if we can identify some of these ways that the modern periodic table is organized. Oops.
All matter is built from 118 essential building blocks known as the elements, and throughout history, many people were set on a path of elemental discovery, while others attempted to create useful ways of organizing them. But it wasn't until 1869 that legendary Russian scientist Dmitry Mendeleev developed an elegant and very useful method, which would later evolve into one of science's most brilliant icons, the periodic table. The periodic table is a super organized collection containing information about each element placed into rows and columns. There are 18 numbered columns on the table that we call groups. These groups are sometimes referred to as families, and like real families, elements in a specific group share some characteristics. For example, elements in group 18 are called the noble gases. These are a collection of elements that are generally very unreactive, like helium and birthday balloons. Next door in group 17, aka the halogens, we find reactive elements that may bond with metals like sodium and potassium to make salts. But what is it that makes different elements share similar chemistry? It's all about the outermost electrons, or the valence electrons. Electrons within atoms are arranged in sets around the nucleus. The set of electrons that is furthest away from the nucleus is the one that interacts with the outermost sets of other atoms, and therefore mostly determines what kinds of chemical reaction that an element does or doesn't do. The periodic table groups elements into columns whose atoms have similar valence electron configurations and therefore similar chemistry. In the case of the halogens in column 17, each of the elements has 7 valence electrons. The noble gases in column 18 all have 8 valence electrons. Now let's take a look at the rows. Each row is called a period, and like the groups, each row is given a number, this time 1 through 7. Within each period, the valence electron configurations of the elements change from element to element since there are more electrons. As a result, we see the chemistry of the elements changing as well. Remember, a different number of valence electrons means a different chemical reactivity. For example, as we move across the second period, the strength with which an element's nucleus pulls on the element's electrons around it increases. Nuclei of elements on the left side of the table pull relatively weakly, so they are more likely to lose electrons in a chemical reaction. Nuclei of an element on the right pull much more strongly, so they are more likely to gain electrons in a chemical reaction. Periodic or repeating patterns of physical and chemical properties are crucial to the organization of the table. These patterns even allowed scientists in the past to predict the properties of as of yet undiscovered elements just by looking at gaps in the table. For example, let's take a look at Mendeleev's original 1869 periodic table.
Okay, we just went over that, so we don't need to do it again in this video. So, right, we've got groups, or their groups are the columns, and they are organized by their similar properties, which equates to they have the same amount of valence electrons. We have the rows, which we'll talk more about in just a second. That equates to the number of electron energy orbitals. And then the third way that I want you guys to know and remember this is just by atomic number. Okay, so we'll talk about this more in a few slides, but atomic number is this little number here. Remember, we learned that in the last chapter. And this little number is just the number of protons that are in the atom, okay? So let's talk about this first way that they're organized, groups or columns, okay? This is a group right here. This is another group. This is one, this is one, this is one, and so on. So these groups are organized together because all the elements in this group have very similar properties. And what Mendeleev didn't know at the time is that this actually equates to the number of valence electrons that each element has, okay? So the video just kind of went over it, but valence electrons are the number of electrons that are in the very outermost shell or energy level, okay? So you can see that here's hydrogen, here's lithium, here's sodium, okay? So in the very outer one, we only have one in this group, okay? Now, like sodium has a lot more electrons than lithium does, but it only has one in the very most outer shell, all right? And then this increases, the number of valence electrons increases in the groups as you go this way from left to right. So everything in this group has one valence electron. Everything in this next group has two valence electrons. And your book, so I'm sure you noticed by now a lot, like every periodic table that you look at kind of displays information in a different way. They follow these same patterns, but for instance, the groups in this periodic table, which is from ptable.com, the groups here are labeled 1 through 18. But that doesn't mean that this row over here has 18 valence electrons, or that this group here has 9 valence electrons, okay? So your book and a lot of other periodic tables also put another group number above each column. So here we see 1A. So your book uses 1A. So the A groups signify how many valence electrons they have. So this group has 1 valence electron. This group has 2 valence electrons. Now this subcategory here of transition metals, you can read this note here. They're weird. They don't really follow the pattern of valence electrons, and there is a very specific reason why. We're not going to learn why in this class, but if you want to know, just let me know and I'll provide more information for you, because it is pretty interesting, but it's way more complex chemistry. If you guys take chemistry as an elective in your junior year, we'll learn why this happens. Okay, so we're skipping over this whole section, right? And then this column has 3 valence electrons, 4, 5, 6, 7, and 8, all right? So you can tell how many electrons, let's say chlorine has, just by knowing that it's in this 7A column, okay? And then your book, these ones, it lists them as 1B. These are all Bs, 1B, 2B, 3B, or whatever, but that doesn't really matter, okay? So what you need to know is that the groups signify how many valence electrons that they have, okay? And that these two columns and these columns are labeled with how many they have, okay? Now to build off of this from the metals lab that we learned, or that we did in class the other day, or if you did it online, you watch this video where it takes all, except for hydrogen, it takes these elements in this first group, in group 1, and it reacts them in water. And what do you remember happening? Well, I'm going to play this clip from it.